HTTP communications are probably the most common communications that you'll see cruising across your network. In this section, we're going to open up a trace file and look at the HTTP packet structure. The trace I'm going to open up is called HTTP-post. Now there's some strange stuff in the beginning of this trace file, and I'm going to skip that till we get down to an HTTP communication after a handshake. So in this trace, we can see the handshake at packet number 25. That's where I want to focus. Packet number 25, we have the handshake going to port 80. There's the SYN, then we see the SYN-ACK, and then the ACK. The next packet is from the client, and it's a GET request. Now the GET request indicates that we want to retrieve data from the server, whereas POST indicates that we want to send data to the server. We'll focus in on this GET request packet right there. I'm going to open up this window just a little bit so we can see a little more about inside the packet. First of all, HTTP runs over TCP, and the default port number is going to be port number 80. Right after the TCP header, the very first thing that we see is the command, the GET command or the POST command or the head command or whatever command is being sent by the client. If we open up this section, if you simply right mouse click and expand the subtree right underneath HTTP, you'll be able to see it all broken out into its individual pieces. The first thing we see is the request method, which is GET. Then we see the URI listed behind that, and in this case we can see this checknews.asp. ASP stands for Active Server Pages. And then the request version. This client is using HTTP 1.1. The accept line says the format or the media type that the user will accept the information in. And then the user agent that's launching this, that's making the request. And this is McUpdate, which is the McAfee update process. And here's the host that the client wants to communicate with. We have some carriage return line feeds just at the end of these lines. And let's go to the response packet where we start seeing some data coming back. Now, packet number 29 is just simply an ACK packet. That's the server saying, okay, I got your GET request. And then in packet number 30, we see a response with a code 200, which means okay. When you go through examining the normal HTTP communications, I'll show you where you can find all of the response codes for HTTP. Here's the server answering back with a response code of OK. The request version is HTTP 1.1, and then we have the response code area here. 200, of course, means OK. And then the server identifies a server type. This is a Microsoft IIS server 5.0. The date, and then there's a line X powered by ASP.NET. Now the content has to do with the content further on down in the packet. There's the data. The content indicates this data. And up above it says content length is 10. And if we count this status, 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10. Each one of those slash ends only takes 1 byte. So the content is 10 bytes long. The content type is text or HTML. And then we see the server setting a cookie at the client. Now the cache control area here indicates who's allowed to cache this information. If it's set to private, only the receiving device is allowed to cache this information. So that's the basic structure. When you go through examining normal HTTP communications, I'll show you what it looks like when files are downloaded using HTTP. In this section, we're going to start out by looking at how to build a capture filter for HTTP traffic, and then we'll go on to building a display filter for all HTTP traffic, and we'll finish up by building a display filter looking for HTTP traffic based on the contents of a specific field in the HTTP packet. First, I'm going to open up the Capture Options window, and I'll open up the Capture Filter area because Wireshark comes with an HTTP filter already built. There are actually 2 HTTP filters. one looking for HTTP traffic going over either UDP or TCP, and one for HTTP traffic going over TCP. Now, HTTP goes over TCP by default, so this second one is the one that is most applicable probably to your network. The syntax is TCP space port space HTTP, and Wireshark recognizes that HTTP will be port 80. I'll click OK and start capturing. And now I'm going to toggle over to a website to start generating some HTTP traffic. I'm on the Wireshark webpage, and from here I'll go to the developer info area, and from here I'll go to the Air PCAP page. And now let's see what traffic I generated. I'm back in Wireshark, and you can see that I was on the Wireshark page, and here I made a handshake and then made an HTTP GET request. I'm going to move this up a bit, and I have TCP segment reassembly on, so you can see that my segments are being reassembled in these packets. There's the GET request, and in the TCP header we can see that the destination port number is 80. I'll close up the TCP header so we can focus on the HTTP portion. There's the whole basic line, there's the summary line for what's happening. It's a GET request for develop.html, to go to the develop.html page using HTTP 1.1. So the request method is a GET, and the URI that's requested is develop.html. This is the request version, HTTP 1.1. Accept indicates the media types that the client will accept information in. And this is the refer. This is where the client was before they made this request. In addition, as I scroll down, we have the language that's acceptable and the encoding that's acceptable by the client, and then the user agent, information about the configuration of the user. There's the host that the develop.html page is on. And then this connection keep alive piece really doesn't make sense anymore with HTTP 1.1. By default, all connections are kept alive unless you put in connection, colon, and then the word close. Now I'll go to the next packet in the trace. Now in this packet, it doesn't feel like we have the HTTP command set in there, but if we look underneath this TCP header, you'll see that we have 1084 bytes of data, and I can see that highlighted down below. So this is how we build a capture filter, and we can see that it looks fine even though we can't see the HTTP information down below. Now I'm going to open up a trace file that has some HTTP traffic, but it also has some other traffic, and I want to filter out just the HTTP traffic and examine that traffic. So I'll stop capturing, continue without saving, and the trace file I'm going to open up is called client dying. And in here you can see that we have a variety of different communications in this trace. In order to filter out all HTTP traffic from an existing trace, or as you're capturing in the background, you want to apply a display filter, just type HTTP in the filter area. And I'll click apply, and now I can see my HTTP communications. There's my GET requests going across the wire. Now we can also build filters just for one area of an HTTP packet, one field in an HTTP packet, such as the request method. We can simply right mouse click and say that we want to prepare a filter based on the selected value, and you can see the syntax up above is http.request.method == quote, and it's got to be in all capital letters, GET. And remember that as you highlight a field, down below in the status line, Wireshark will tell you what the syntax of that field is in case you want to build a filter on it. There's the request version information, the user agent information, the host information, etc. I'll show you the two places that you can get the display name syntax for making filters. The first location is on the Wireshark web page. We go to the documentation section and select display filter reference, And this time I will select H, and I will look up HTTP. And here are all of the field names that can be used for creating HTTP display filters. So we can see there's the referrer, there's the request method, there's the request version, the response codes. When we get into the section on analyzing normal HTTP traffic, I'll show you a master list of HTTP response codes. From within Wireshark, we can also figure out what display filters are available to us for HTTP by selecting expression and then typing in HTTP, opening up this selection. As we scroll down, we can see what's available to us. So we may want to do HTTP response code equal to and put a value, or HTTP, let's see, refer contains a certain value, a string, or the HTTP request method equals a certain value, or HTTP request, it's true or false. Now we're going to look a little further into normal HTTP communications. I'm going to start with the normal process of downloading files to your system. So when you web browse, you're getting files and bringing them down to your system. And then I'll show you what it looks like when you post information up to a web server. The first trace file I'm going to open up is called http-espn.pcap. And this is a web browsing session to the espn.com website. We can see it starts out with a DNS query, and then we have a three-way handshake process. Everything seems to work fine so far. Bring this window up. Now there's our get HTTP request. I'm going to collapse the TCP header because I don't really care about the TCP header. There's our request to get, and I want to get the root page there. The request is HTTP 1.1, and the accepted media types are all. Accepted language is English, and coding is gzip and deflate, and the user agent provides its information. There's the host that the client is on, and as we know, keep alive doesn't even make any sense because by default the connection will be kept alive, unless you say connection close. Scroll down, I'll see the server send back a simple ACK packet. Now we do have some problems with this connection, where some of the communications were lost. So I'm going to scroll down until we get the answer from the server. And here's the reply from the server. The server sends back a code 301, which says moved permanently. There's the response code number 301. And I'll take you out now to iana.org, where we can see the whole list of response codes. I'm on the iana.org website, and I'm going to go to Protocol Number Assignment Services. Then I'm going to hit the letter H, and here we can see Hypertext Transfer Protocol status codes, HTTP status codes. I'll click on that, and here's the list, the master list of status codes for HTTP, and there's our 301 moved permanently. And it tells you that this is documented further in RFC 2616. Now this area in IANA is a living document area, so don't just download these things and keep them in a binder somewhere, because some of these things change over time. We're probably all most familiar with the 404 message, the file not found message, or the general not found message. What we want to see all the time, of course, would be the 200, which is OK. Now let's go back to our trace file. The ESPN server has told us that the file we're looking for has moved permanently, and here is the date of this capture, and then the server is an Apache server, and it tells us the location of where we should go to get the file. We need to go to espn.go.com. Content length is telling us how many bytes are in this section down below, the data section. connection close. Okay, here's an example where this server is saying, okay, now this connection is going to be closed because you're not going to be communicating with me anymore. It's forwarding us on to another server. And then the content type down below is text or HTML format. There we can see the content below. Moved permanently. This document has moved, except that our browser isn't even going to show us that information. We're going to go straight over to the new site. Our client says, ACK, thanks very much for the information. And then the client makes a DNS query to get to espn.go.com. Meanwhile, our client is also closing down the connection to the previous server. Now, we have the DNS response that says that espn.go.com is at 199.181.132.244. So now we see the three-way handshake connecting to the new server. Finish up the three-way handshake. And when you're looking at HTTP communications, one of the things you have to watch for is that we will see these different connections sort of intertwined. So you need to pay attention a little bit to the port number, the dynamic port number that the client is using to make sure that we're not looking at multiple communications. So the previous communication, the user was using port 3879. In this communication to espn.go.com, our client is using 3881. So there's the handshake process, and then our client sends out a GET request to the server. Here's the GET request, the client trying again, saying, listen, I'd really like to get the root page. Provides all the same information that it sent before, and now we get information back from the server. Now at this point, the server begins streaming data down to our client, and we could see it all down in this data section. If you end up spending a lot of time looking down in that data portion of the Wireshark window, remember that you can right mouse click and say that you want to follow the TCP stream. And Wireshark will color code the conversation based on who said what. So anything in red by default is going to be from the client to the server. Anything in blue is going to be from the server to the client. And now this is the information coming down from the server. So we can see the server says it's a Microsoft IIS server. We can see it setting a cookie. We can see it tell us when the cache expires. We can see it giving date, accepted ranges in bytes. And there's the cookie being set. And as we scroll down, you'll see warning 214 espn.go.com, redline networks. And there is the data coming down to the client. Now these guys stream a bunch of video down to you when you connect to their site. So I'm going to close this window. I'm going to clear out our filter because we want to see if there are any other connections involved in this process. So this is all the data streaming coming down from the HTTP server. Now all of a sudden we see the user make another connection to espn-ak.starwave. We get a DNS response, and there's our handshake process, and we make a request to get the style sheet information. Server comes back and begins to stream the information. Well, not yet. First, we have to make handshake, another handshake. Now we've got multiple connections going on to the same server. That server is ending in a .17. So here we've made our request to get insert files. Scroll down, we see another request. Java, front page. Scroll down even more, and we'll see what happens after this information is loaded down to the client. Now we've got some lost segments in there. And there's the client going for yet another DNS query to connect to a different server. And on that server, the client is asking for a JPEG file. Again, at any point you can right mouse click and say that you want to follow the stream so that you can see what's being transferred across the wire. Scroll down. There's the data coming down. And remember, I have reassembly on. So here we can see there's a request for logo. Let me go back up to the one before it. There's our request for the JPEG file. There's the JPEG file. You know, the interesting thing is that we can rebuild that JPEG file. We can highlight the entire JPEG file. Oops, I went a little too far there. Highlight the entire JPEG file and then Control-C to copy it and then paste it over into a text file, just making sure that we end it with .jpg. That was one of the tasks that you learned in the Wireshark University Fundamentals and Functionality class. I'll scroll down more and I can see there the client is going after another image, more information. And this is really nice because, again, if you spend a lot of time and you're looking down here to try to figure out what this communication is all about, you can easily just right mouse click and look at what's being transferred across a connection. And this filter is based on not only addresses, but also the port numbers. So there we can see port number 3881 and port number 80 communicating. I'm going to clear that filter and show you one other way to pull out the connection that has the most data exchanged. You can select Summary, Conversation, go to TCP, and then sort according to the bytes column. Here we can see the majority of traffic went across port 3884 from the client. I'll right mouse click and apply this as a filter based on the selected going both directions. Now I want to see this without having to scroll through here. So I'll right mouse click and follow the TCP stream. And we can see what's being transferred across that line. We can scroll through, see there we're getting web pages down. Lots of information coming down. Most of the time when people complain and say that web browsing is too slow, most of the time it's not the HTTP session's fault. Most of the time we have an underlying problem with TCP, or maybe we have a rights issue to the page. Luckily with HTTP communication you'll be able to see those codes come back to say, I'm sorry, you don't have rights to this, or yes, you do have rights to this. In the next section, I'm going to focus on some problematic HTTP communications. But before we go on to that, I want to show you what it looks like when someone does a post operation. So I'm going to open up a trace called HTTP-post. Now, we're not going to pay attention to the beginning of the trace because the beginning of the trace is strange, and I'll talk about it in the next section. We'll go down all the way to packet number 25, where we see a handshake to a server on the HTTP port, and then we see a client making a GET request. So the client is requesting checknews.asp, ASP standing for Active Server Pages. See the server came back with an OK. Now, not long after that, the client posts information. So now data is going from the client up to the server. If you pick up traffic from a system, and that system should not be sending data up, look for this post stuff going up on the wire. This just happens to be the McAfee update process. And I can tell that by opening up the HTTP portion of this packet a little further. Open this up. And we can see that the user agent is McHTTP, and the host that I'm on is us.mcafee.com. But if we did someday see a post operation and we saw the user agent as something we didn't recognize and the host is something that we didn't intend to connect to in the background, then it means we probably have some malware, some virus, some worm on the local system. Now, there are some times when you're analyzing traffic where you'll be looking at the traffic and you'll ask a user to go out to a website and you want to see how the performance runs. And they've been complaining about performance. But when you look at the trace file, you don't see what you expect to see. You're not seeing the big file transfer go across the cabling system. Well, it might be because the client should have the information in cache. So let's go take a look at what that looks like when we're analyzing the traffic. The trace file I'm going to open up is called web browse OK. And in this trace, we have the three-way handshake first, and then we see the client make a GET request. Now, I'm going to get rid of the packet bytes down below so we can see more information. Now, here's the request. It's a GET request for the root page using HTTP 1.1. There's the language information, there's the encoding information, and here is the if modified since entry. It says if modified since Saturday the 16th of March 2002 at 7:16 Greenwich Mean Time with a length of this value, then give it to me. But if it hasn't been modified, the client's trying to say, I've already got it. Now, I picked up this trace file a long time ago. Look at that, March 2002. But it works exactly the same way today. If you capture a trace of yourself going to a web page, go back and browse that web page again just moments later. In the second browsing session, you should see this if modified since entry, and you shouldn't see that your system goes and downloads that information. Here we can see the server answering back, an ACK, and then it comes back with a 304 saying, no, it has not been modified since that date. So the client doesn't need to go and get that file, the root page, and the client finishes up the communication. That's what it looks like, and again, the entry there that's the key entry is that if modified since. And when you see that, again, the client's got it in cache. At this point, you want to clear out the client's cache and then have them go to the web page again so you can see how it performs. Because they may have had a hard time getting the file the first time, but the second time, they're not even going and asking for that file again. They already have it on their local system. Now in the next section, we're going to focus on some unusual HTTP communications. We'll look at what it's like when you go to a website and they have so much advertising on there that they're redirecting you around to their advertisers, or maybe they have a 404 file not found. They're actually going to blame you, the client, for that. Then we'll look at an unusual post session going on. The difference between a normal post session and an unusual post session. We'll focus on both of those in one trace file. And we'll also look at this really strange process of connecting to an HTTP server, but not actually transferring any data, just making the connection over and over and over again. Now in this section, I'm going to show you some unusual HTTP communications. Now, in the first communication, we're going to look at when you go to a website and it redirects you all over the place. So this is http://espn.pcap. And without even really going through what's happening in here, I'm going to open up statistics, HTTP, and the requests area. Now, all I did in this trace file was I filtered on traffic to and from the client hardware address. So that's the only thing I should be seeing in here. I'll create the statistic. And look at that. When you say you want to go to just espn.com, these are actually all the different websites that you go to. Look at all of those. Now I want to know a little bit more. And we can look inside of these and we can see how many files we're getting from each of these locations. So this is all from espn.go.com. espn.com, sorry, you tried to get the root there, but unfortunately that was a redirection. So I'm going to close this out, close this window out, and go under Statistics, HTTP. This time I'm going to look at the packet counter area. Now I'm not putting in any filter because I pre-filtered my traffic when I captured it. So there we have 12 HTTP packet requests and 278 HTTP response packets. And out of those, we can see that we have 8 redirections. I'll click Open. Now here's where we have the codes. Now 301 means moved permanently, and 302 actually means moved temporarily. So that is a redirection. Then we can see some client errors. And look at that. The client errors, 404 not found. It's not my client's fault that it was told to go to a page where something didn't exist, but it's always seen as a client error because you must have selected the wrong page. So those are part of the reasons why it's very slow to browse to the ESPN webpage, because you have all this redirection in there and a client error, and you also go to so many different sites when you're just trying to get the basic sports information from ESPN.com. The next trace I'm going to open up is from, it's called Evil Program, and I want you to see a system reinfecting itself using HTTP. I'm going to use my HTTP filter. Now, the traffic at the beginning of this all has to do with McAfee. The client is going through the McAfee update process, and we can see that if we look inside of the packets. We can see the user agent McUpdate and the host is us.mcafee.com. Now we do post information up to mcafee.com to say what the state is of our virus detection software, what the current level is, the revision level that we're on. But as I scroll through here, I see another post going on. There's another McAfee post. Remember, I want to watch who is this post going to. Scroll through, there's McAfee again. Get request, there's McAfee again. So far so good, everything seems all right. Another McAfee. Now we see a GET request for an executable called bkinst.exe. And I can see by looking at the HTTP packet that this is coming from the host virtumon.com. And I didn't choose to go to virtumon.com, so I don't know why my system is going to virtumon.com. And this was an infected system. Now, let's look here. I'll take you a little further into this communication so you can see what happened. So here we can see the basic information. We're going to virtumon.com, and right after that the client does a post. And in here you'll see some interesting fields. G version, G setup ID, G affiliate ID, URL, client, crash history, client GUI ID, gzip supported, UID, user agent. Okay, we expect to see user agent, and the host information and the content length and the cache control. But what is all this G dash other stuff that the client is asking, is sending up to the server? It doesn't appear like there's valid data in those fields either. So let's look at what the server sends back to the client. Now we see these G category, add category sum, connections per day 2, the date, the pop-ups per day 24, statistics upload delay 1. So all of this stuff has to do with the malware that was sitting on that system. The system would actually go and reinfect itself every day by going and getting this bkinst.exe file, downloading it to the local system, and then it would post information about itself and get its latest settings. And that was all done over HTTP. Again, you really need to watch the HTTP post communications on the network to make sure that something isn't going out that you don't want to go out. Now here's another strange communication, and this is called http-post.pcap. Now this is the McAfee update process, and I'm going to get rid of my HTTP filter because I also want to see the handshake packets. So I'm going to clear out that filter. Now I'm looking at all of the traffic, including just the handshake processes. An interesting thing with this is that this is the McAfee server, this 216.49.88.118. And when you do an update process with McAfee, you begin by doing something I call the McAfee dance, where you make a connection to the server. So we see SYN, SYNAC, ACK, and then you shut that connection down. FNAC, FNAC, ACK. And you do that 4 times in a row. SYNAC, SYNAC, ACK, FNAC, FNAC, ACK, SYNAC, SYNAC, ACK, FNAC, FNAC, ACK. SYN, SYNAC, ACK, FNAC, FNAC, ACK. And then you go on to making a handshake that you'll actually use. It's a very strange process that takes place at the beginning because no data is exchanged at all. It's just we touch the server 4 times and then we say, okay, now we're ready to talk. It's a very strange thing to see. I would highly recommend that you baseline your HTTP communications so you know what's normal today and you can go back later and detect when something strange is occurring in your communications.